Some ancient buildings have survived earthquakes for over 2,000 years. They stand as monuments to a forgotten science of resilience, constructed long before modern steel and concrete. This is the story of how ancient engineers mastered earthquake-resistant architecture, using little more than simple tools and a deep understanding of the natural world. By the end, you will possess a new framework for understanding how to build in harmony with the Earth's forces. How did entire civilizations develop a shared secret to outsmarting seismic chaos? And why have we only recently begun to relearn their methods? What do you believe is the most important lesson we can learn from the builders of the past? The Parthenon stands almost defiantly upon its Athenian hill, its marble columns having shrugged off countless tremors for more than 2 millennia. Meanwhile, modern cities with all their steel and concrete have crumbled in the face of lesser seismic forces. This stark contrast presents a profound historical puzzle. How could ancient builders, working with primitive bronze and stone tools, consistently achieve a level of resilience that often eludes our own advanced engineering? This was not an isolated miracle of Greek genius. From the towering pagodas of Japan that sway like trees to the impossibly precise stonework of Inca walls in Peru and the massive, self-aligning foundations in ancient Turkey, we see the same story written in stone across the globe. These were not random acts of sturdy construction. They were the result of a deliberate and highly developed science, a collective wisdom born from observing the Earth's violent language. The true secret was not found in the chisel or the hammer, but in the mind of the engineer. These master builders possessed a deep, intuitive grasp of physics, understanding how forces move through materials and how structures could be designed to dance with the Earth rather than fight it. They learned to build with nature, not against it, and that foundational insight is what we are only now beginning to fully appreciate and relearn. A tall reed bends in a storm while a mighty oak snaps. This simple observation of nature lies at the very heart of ancient seismic wisdom. Ancient builders understood that you cannot defeat an earthquake's raw power with sheer rigidity. The Earth will always be stronger, so they chose a different path, one of harmony rather than conflict. They designed their structures not to stand perfectly still, but to sway, to rock, to dance with the ground's violent motions. This principle of dynamic response was their masterstroke. It meant that when the Earth shook, the energy of the quake was not absorbed by the building in a single, destructive blow. Instead, that energy was transformed. It became the very motion that allowed the structure to survive, channeled through carefully designed joints and connections that let the building move as a cohesive, flexible unit. Think of it like a palm tree in a hurricane, its trunk and fronds flowing with the wind, dispersing that immense force safely. This philosophy stands in stark contrast to many modern rigid structures that, until recently, were designed to be immovable. When faced with an earthquake, such a building tries to resist completely, and if the shaking is strong enough, that resistance fails catastrophically. The ancient engineer's first line of defense was therefore not strength, but intelligent flexibility. This foundational concept of controlled movement paved the way for the brilliant, specific architectural features that brought this principle to life. One of the most brilliant applications of this flexible philosophy can be found not in the walls, but in the very foundations of ancient structures. Picture a massive stone temple resting not on solid bedrock, but on a carefully prepared bed of rounded stones. When the earth begins to tremble, the entire building is able to slide and shift ever so slightly atop this layer, moving independently of the violent shaking below. This is the principle of base isolation, a concept that feels remarkably modern, yet was masterfully executed by Inca engineers at sacred sites like Ollantaytambo. They achieved this by creating what were essentially the world's first sliding foundations. Between the building and the ground, they would place a layer of loose gravel, sand, or specially shaped stones that acted as natural ball bearings. This simple layer performed a miracle of physics. It effectively decoupled the heavy structure above from the high-frequency, jerking vibrations of the earthquake. Instead of those destructive forces traveling directly up into the walls, they were largely absorbed and dissipated by the shifting, rolling stones below. The building would experience a gentle, rocking sway rather than a violent, bone-jarring shake. The sophistication of this passive damping system, engineered with nothing more than rocks and sand, is truly staggering to contemplate. It required a profound understanding of how energy moves through the earth and how to interrupt its path. This foundational genius allowed entire complexes to survive for centuries in one of the most seismically active regions on the planet, proving that the most powerful solutions are often elegantly simple. But achieving that flexible foundation was only half the battle. The structure built upon it had to be perfectly aligned to move as one unified body. Without sophisticated technology, ancient engineers turned to two of the most elegantly simple tools ever invented, the plumb bob and the level. A plumb bob is nothing more than a weighted object suspended from a string, yet in the hands of a skilled artisan, it became an infallible guide to true vertical. Gravity would pull the weight straight down, creating a perfect reference line against which every column and wall could be aligned. For establishing a flat plane, they used the water level, a principle based on the unshakable fact that water always finds its own level. By digging a shallow trench around a construction site and filling it with water, or by using a long, water-filled tube, they could transfer a perfectly horizontal line across vast distances, ensuring that the foundational base was flawlessly even. This obsessive pursuit of precision was far more than an aesthetic choice. It was the key to structural survival. In an earthquake, forces travel through a building seeking out weaknesses. A single wall that is even slightly out of plumb, or a foundation that is not perfectly level, creates a point of concentrated stress. When the shaking begins, the energy will violently exploit that tiny imperfection, leading to a crack, a tilt, and potentially a catastrophic collapse. By ensuring every element was in perfect vertical and horizontal alignment, the ancient builders guaranteed that seismic forces would be distributed evenly throughout the entire structure. The building could then sway and rock as a single, cohesive unit, dissipating the energy harmoniously instead of breaking apart at its weakest link. The true mastery is witnessed in the results, with stone blocks fitting together so precisely that you cannot slide a piece of paper between them, achieving tolerances that would challenge many modern masons even with their advanced laser guides. This was a triumph of profound skill over complex technology, proving that the most critical tool was not the device itself, but the deep understanding of the principles it represented. Those perfectly aligned walls needed more than just precision to survive. They needed immense strength. Across continents, we see ancient engineers consistently reaching for the same solution, building walls of staggering thickness and weight. The colossal ramparts of Heimji Castle in Japan, or the heavy, tapering walls of Romanesque churches in Europe, were not merely for show or for defense. They were performing a hidden function, acting as the structure's primary shock absorbers. This is the principle of mass damping in action. Think of a massive ship riding out a storm. While smaller boats are tossed about violently, the ship's huge mass allows it to plow through the waves with a steady, stable motion. It dampens the violent motion. Ancient builders applied this same principle to their architecture. The sheer weight and inertia of these massive walls meant they resisted rapid movement. When an earthquake's high-frequency vibrations tried to shake the building, the walls simply would not respond to that frantic energy. Their immense mass acted to slow everything down, transforming the rapid, destructive shaking into a much slower, more manageable rocking motion. This was a brilliant, intuitive grasp of vibrational physics. The builders understood that by increasing the mass, they were increasing the structure's inertia, its resistance to changes in motion. The seismic waves would expend their energy trying to move these monumental walls, and in the process, their destructive power was dissipated as harmless heat and sound within the stone itself. This is why so many ancient fortresses and temples feel so solid and permanent. Their survival is not just a matter of sturdy materials, but of a profound design philosophy that used weight itself as a shield against the Earth's chaos. This strategic use of mass created a powerful, stable base, but the true genius was in how they connected everything at the very top. The final piece of this ancient puzzle lies in the very stone itself. Before a single block was ever set into place, a master builder would walk through a quarry, his hands reading the stone like a book. He was not just looking for size or color, he was assessing the stone's soul, its hidden character. He searched for dense, fine-grained rock that could absorb tremendous energy without shattering. He avoided stone with visible fault lines or weak planes that would crack under stress. This was a deep, intuitive form of material science, a knowledge passed down through generations of artisans. They understood that the stone's journey from the earth was just as important as its placement in the wall. Once the perfect block was chosen, the shaping began. With nothing but bronze or stone chisels and wooden mallets, the masons would begin their meticulous work. This was not a process of brute force. It was a slow, deliberate dance of percussion, tapping and shaping the stone to reveal its final form. Each strike was calculated, following the natural grain to avoid creating hidden fractures. The goal was a perfect polygonal shape, with multiple angled faces that would lock tightly against its neighbors. The time invested in this shaping process did more than just create a beautiful wall. It fundamentally enhanced the structure's seismic resilience. A perfectly fitted stone with multiple points of contact distributes any load or shock wave evenly across a vast network of blocks. When an earthquake strikes, the energy cannot find a single, weak point to exploit. Instead, it travels through the entire wall, diffused and shared by thousands of interlocking joints. The wall moves and flexes as a single, monolithic entity. This intimate, hands-on relationship with their materials is something we have largely lost in the age of mass-produced concrete and steel. The ancient builder knew his stone, he understood its strengths and its secrets. This profound connection between craftsman and material, this reverence for the very substance of the earth, was the final, crucial ingredient that allowed their creations to defy the centuries. That jagged, puzzle-like wall is a masterpiece of seismic engineering. Each stone, with its complex, multi-angled faces, locks perfectly with its neighbors in a three-dimensional embrace that requires no mortar. This is the principle of interlocking masonry, and its genius lies in how it manages force. When an earthquake sends violent shockwaves through such a wall, the energy has nowhere to go. It cannot travel in a straight line to create a single, catastrophic crack. Instead, the shaking force is immediately broken up and redirected. Each time a shockwave meets one of those intricate joints, it is split into dozens of smaller, weaker forces that travel in countless new directions, distributing the stress evenly across the entire structure. The wall essentially moves as a single, flexible skin, with the stones constantly readjusting and settling against one another, absorbing the energy through friction and movement. When the shaking stops, they simply settle back into their original locked positions. This is why you cannot slide a knife blade between them. The fit is too perfect. This dry stone construction demanded an almost superhuman level of precision. How did they achieve such perfection with only stone hammers and sand for abrasives? The process was one of relentless trial and error. A mason would spend days, perhaps weeks, on a single block, repeatedly placing it against its neighbors, identifying high spots, and then patiently grinding them down with sand and water until the contact was flawless. This was not just construction, it was a form of slow sculpture, a dialogue between the craftsman and the stone. The result was a wall that was not rigid and brittle, but alive and dynamic, a unified entity that could dance with the earth and remain standing for 1,000 years. This profound understanding of how to turn a wall into a cohesive, flexible unit represents a monumental achievement in human intuition, one where the builder's knowledge was literally set in stone. A pyramid is perhaps the most stable structure ever conceived by the human mind. Its wide base and narrowing form naturally push weight downward and outward, creating a perfect equilibrium that defies collapse. Ancient engineers intuitively understood this geometric power, choosing shapes that inherently channeled destructive forces safely into the earth. Beyond the pyramid, two other forms became cornerstones of seismic resilience: the arch and the dome. The secret of the arch lies in how it manages compression. When weight presses down on a classic rectangular doorway, the force pulls apart at the bottom, creating a weak point that can easily fail. But an arch transforms that same downward force. Each wedge-shaped stone in the arch pushes against its neighbors, transferring the load sideways into the supporting walls or columns. This creates a continuous chain of compressive strength, a powerful flow of energy that the materials are perfectly suited to handle. The dome is simply an arch rotated around its center, creating a strong, continuous shell. This elegant form distributes any point of stress across its entire curved surface, whether the load comes from above in the form of its own weight, or from the side during an earthquake's lateral shaking. Think of it like an eggshell, incredibly thin yet remarkably strong because of its curved geometry. The Romans perfected this with their vast, unsupported concrete domes, but the principle was understood and applied by builders across the ancient world. What is truly remarkable is that these incredibly robust frameworks were constructed with the simplest of tools: wooden templates to shape the stones and measuring ropes to lay out the perfect curves. They were not building mere shapes, they were constructing a skeleton of strength, a geometric logic that provided a resilient framework far superior to a simple, vulnerable box. When the ground shook, these forms did not fight the forces, they guided them, creating a graceful and unbreakable dance between architecture and the raw power of the earth. Sometimes the strongest defense is a planned retreat. Ancient engineers understood that a building, like a living thing, must sometimes yield in one place to survive as a whole. This led to one of their most counterintuitive strategies: the deliberate creation of intentional weak points. Imagine a modern electrical system with a fuse. When a power surge occurs, the fuse blows, sacrificing itself to protect the entire expensive appliance. Ancient builders applied this same logic to their architecture, designing specific elements to act as structural fuses. These were not flaws but brilliant planned failure points. When seismic forces became overwhelming, these sacrificial components would be the first to give way, absorbing and dissipating the destructive energy in a controlled manner. This prevented that energy from traveling through the entire structure and causing a catastrophic, total collapse. The building would be damaged, but it would remain standing, its core integrity preserved for repair. This concept of planned deformation reveals an almost philosophical depth in their thinking. They were not trying to build something eternally immutable, but something resilient, something that could bend and even break in a calculated way to live on. A perfect example of this is found in the graceful, multi-tiered pagodas of Japan. At the heart of these towering wooden structures is a central pillar, but it is not anchored rigidly to the frame. Instead, it hangs like a massive pendulum or rests in a stone base that allows it to swing freely. When an earthquake strikes, the pagoda's flexible wooden frame sways in one direction, while this heavy central pillar sways in another, its inertia acting as a counterbalance that absorbs and dampens the shaking energy. The joints and connections are designed to flex and groan, acting as a network of small fuses that release stress. This brilliant design allows the pagoda to dance with the quake, its movements canceling each other out, ensuring that even the most violent tremor results in a graceful sway rather than a splintering crash. It is a breathtaking demonstration of controlling chaos by inviting it in, a lesson in strategic sacrifice that we are still learning from today. High in the Andes, the stone city of Machu Picchu seems to defy gravity itself. Perched on a razor-backed ridge between two towering peaks, this ancient sanctuary exists in one of the most seismically active landscapes on Earth. For over 5 centuries, it has endured countless tremors, not by chance, but through a symphony of engineered solutions that transformed the mountain's weaknesses into strength. The first and most visible of these is the breathtaking network of terraces that cascade down the steep slopes. These were far more than just agricultural platforms. Each terrace was a massive retaining wall constructed with that same masterful, interlocking stonework, but their hidden function was genius. They acted as a giant comb, breaking up the slope and holding the mountainside firmly in place. During an earthquake, the land wants to slide and flow downhill in a phenomenon known as a landslide. The terraces prevented this by compartmentalizing the slope, confining any potential ground movement to small, manageable sections. The shaking energy, instead of building up and unleashing a catastrophic landslide, was dissipated across thousands of these stone barriers. The city itself was built upon this stabilized, stepped foundation, a masterpiece of preemptive ground control. Yet, even a stabilized slope is not enough to anchor a palace. For that, the Inca builders went deep. The foundations of Machu Picchu's most important structures are not shallow. They extend far into the earth, with massive cornerstone blocks sunk directly into the stable subsoil. This technique, known as deep foundation construction, bypassed the loose, unstable topsoil that could shift and slide during a quake. The buildings were literally tied to the mountain's bedrock, allowing the upper structures to sway as a single, anchored unit while the ground beneath them churned. This combination of terracing and deep anchoring created a stable platform in an inherently unstable location. But the Inca engineers had to solve one final, invisible threat: water. They understood that saturated ground turns into a deadly slurry during an earthquake, a process modern engineers call liquefaction. To defeat this hidden danger, they built one of the most extensive and sophisticated drainage systems of the ancient world. Beneath every terrace, under every building, and lining every street, you will find layers of crushed stone and expertly carved drainage channels. This network acted like a subterranean circulatory system, capturing rainwater and groundwater and channeling it swiftly away from the foundations. By keeping the soil perpetually dry and well-drained, they ensured the ground maintained its friction and strength, refusing to turn to liquid when the earth began to shake. The survival of Machu Picchu is no accident. It is the direct result of this holistic, multi-layered defense strategy. The terraces stabilized the slope, the deep foundations anchored the buildings, and the drains kept the earth solid. Executed with nothing more than bronze tools and stone hammers, this cloud-shrouded city remains the ultimate living textbook of how to build in harmony with a trembling world. Every collapsed wall told a story, and every fractured column held a lesson. For ancient engineers, failure was not an ending, but the most critical phase of their research and development. They did not have computer simulations or seismic testing labs. Their laboratory was the real world, and their data came from the rubble of past earthquakes. When a building fell, master builders and their apprentices would walk through the ruins, their eyes tracing the lines of fracture. They were asking fundamental questions. Did the wall fail at the joints? Did the foundation shift? Which part of the structure gave way first? This meticulous post-disaster analysis was their primary tool for innovation. A technique that worked for a minor tremor might be completely inadequate for a major one. Each new collapse revealed a previously unknown weakness, a hidden flaw in their design logic. This process of observation and adaptation was brutally slow, unfolding not over years but over generations. The knowledge gained from one catastrophic event would be integrated into the rebuilding, leading to a slightly stronger, more resilient design. This refined method would then stand until the next great quake tested its limits once more. This was a long-term, empirical approach where success was measured in centuries. The architectural principles we now admire were not born fully formed. They were forged in the fires of repeated failure, each collapse chipping away at the stone of ignorance until only the most resilient techniques remained. This cumulative wisdom became a sacred trust, passed not through written manuals, but through the intimate teacher-student relationship of the apprenticeship. A young mason would spend decades at the side of a master, learning not just how to cut a stone, but why a certain angle made it stronger. He would hear the oral histories of great collapses and the legendary structures that withstood them. He learned the stories behind the rules, the real-world reasons for every design choice. This living tradition ensured that hard-won knowledge was not lost, but was instead refined and improved with each successive generation. The master builders were not just constructing buildings, they were building upon a legacy of proven solutions, a vast collective intelligence written in stone and memory. Look at the flawless symmetry of a Greek temple, its columns and walls mirrored perfectly on either side of a central axis. This visual harmony was far more than an artistic choice, it was a profound seismic defense mechanism. Ancient engineers understood that an unbalanced building is a vulnerable building. When the ground shakes, a structure with an uneven distribution of weight or stiffness will not sway as a single unit. Instead, it will twist, a violent, wrenching motion that places unimaginable stress on the connections and materials. This twisting, known as a torsional force, is one of the primary killers of buildings in an earthquake. It literally pulls the structure apart from the inside out. A symmetrical design, however, creates a perfect alignment between its center of mass, the point where its weight is concentrated, and its center of rigidity, the point around which it naturally wants to resist twisting. When these 2 points are one and the same, the building responds to seismic forces in a predictable, uniform manner. It sways back and forth as a cohesive whole, with every part of the structure moving in concert, effectively canceling out the destructive torsional forces before they can even begin. This principle of balance was achieved not with complex calculations, but through an intuitive application of simple geometry and proportional systems. The builders used sacred ratios like the golden mean to dictate the relationship between a building's width, height, and depth. These timeless proportions ensured that the final structure was not only beautiful to the human eye, but perfectly balanced in the face of the Earth's raw power. The elegant columns and perfectly spaced portals of these ancient temples were not just elements of design, they were carefully calibrated components in a massive, life-saving instrument. The pursuit of beauty and the imperative for survival were, in their world, one and the same. Across the Pacific and centuries earlier, another culture was weaving flexibility into the very bones of its buildings, not with stone but with wood. In the temples and pagodas of Japan and the great halls of China, we find a wooden skeleton of astonishing complexity, a framework designed not for rigid permanence but for graceful, life-saving movement. The secret lay in the joints. Master carpenters developed an intricate language of interlocking wood, using techniques like the penetrating tie beam known as the nuki and the timeless mortise and tenon. A mortise is simply a slot or a hole carved into one piece of timber. A tenon is a protruding tongue, meticulously shaped on the end of another beam to fit perfectly into that slot. When joined, they create a connection that is both incredibly strong and subtly flexible. These were not nailed or glued rigidly in place. Instead, they were crafted to allow for a tiny, almost imperceptible amount of play. When an earthquake struck, this was where the magic happened. The entire wooden frame would sway and rock, and the energy of the quake was transformed into friction and movement within these thousands of individual joints. Each connection acted as a miniature shock absorber, its slight grinding and shifting converting the destructive force of the tremor into harmless heat and sound. The building would groan and creak as it moved, a chorus of wooden parts working in concert to dissipate the energy safely. This was a dampening system built entirely from wood and precise craftsmanship. Using only hand saws, chisels, and wooden mallets, these artisans created a structural resiliency that rivals modern engineering. It is a profound testament to how different material cultures, one working in stone and the other in timber, independently arrived at the same universal truth. To survive the Earth's violence, a structure must not resist, but must learn to move. The ground itself was their first and most important blueprint. Before a single stone was laid, ancient engineers engaged in a profound dialogue with the landscape, understanding that the Earth's hidden composition could either amplify an earthquake's fury or soften its blow. They learned through painful experience that structures built on soft, waterlogged soils would suffer the most violent shaking, as the loose ground acts like a bowl of jelly, magnifying the seismic waves traveling through it. In contrast, stable bedrock or dense, well-drained soil provides a firm, direct connection to the Earth's crust, allowing shockwaves to pass through with far less destructive amplification. This critical insight guided their very first decision where to build. They became master geologists without a formal science, reading the land for clues. They looked for rocky outcrops, observed the types of plants that thrived in well-drained areas, and learned from the oral histories of elders which valleys had trembled most violently in past events. This was not a random guess. It was a careful selection process based on centuries of accumulated local knowledge about the land's unique personality and its seismic history. When the ideal naturally stable site was not available, they did not simply build on the weak ground. They reshaped the earth to meet their needs. They carved vast terraces into unstable hillsides, as seen at Machu Picchu, to create a series of level, reinforced platforms. In other cases, they would painstakingly cut away soft topsoil to reach the firm substrate beneath, or even construct massive stone platforms and infill them with compacted rubble to create an artificial, stable hill for their sacred structures. This holistic approach meant the building did not simply sit on the land, it was an extension of it. The foundation was not an afterthought, but the culmination of a deep environmental wisdom, a first and critical step in a multi-layered defense system that began with choosing the right partner in the eternal dance with the earth. Listen closely to the sound of an ancient wall during an earthquake. It would not be the splintering crack of failure, but a low, grinding hum, a chorus of countless stones whispering against one another. This sound is the audible signature of one of the most brilliant principles in ancient engineering: energy dissipation through friction. Within the meticulously fitted, mortar-free walls of the Inca, or the layered stone foundations found across the ancient world, the tiny gaps between blocks were not empty spaces. They were dynamic theaters for a fundamental physical force. When the ground shook, these stones did not remain perfectly still. They shifted, they rocked, they slid against their neighbors in movements almost too small to see. And with every microscopic movement, they generated friction. This friction was not a design flaw or an unintended consequence. It was the entire point. It acted as a built-in passive energy dissipation system. The violent, chaotic kinetic energy of the earthquake, the energy that seeks to tear a building apart, was being constantly transformed. As the stones rubbed together, that destructive kinetic energy was converted into a different form: heat. It was quite literally being bled off, dissipated harmlessly into the atmosphere, before it could accumulate to a level that would fracture the stone or collapse the wall. Think of it like rubbing your hands together vigorously on a cold day. The motion of your hands creates heat, warming your skin. The energy of your movement is transformed. The ancient wall does the same thing on a monumental scale, using the earthquake's own power against itself. This was a damping mechanism that required no maintenance, no moving parts, and no human intervention. It was always on, always ready, a silent guardian built into the very fabric of the structure, born from a profound understanding that sometimes the best way to defeat a giant is to let it exhaust its own strength. These architectural secrets did not simply emerge from the stone itself. They were born from the minds and hands of a dedicated class of artisans, the master builders. This deep, intuitive understanding of physics and materials was not written in books, but was guarded and transmitted through a living human network, the craftsmen's guilds. Within these guilds, knowledge was a sacred trust. A young apprentice would spend years, often a decade or more, under the watchful eye of a master. His first tasks were not cutting stone, but mixing mortar, carrying tools, and observing. He learned by doing, by watching, and by listening to the stories of past projects and legendary collapses. This was not a fast education. It was a slow transformation, a process of absorbing a way of thinking as much as a way of building. The master was not just teaching how to shape a block, but why a specific angle made it stronger, why a certain stone was chosen for a foundation, and how the entire structure would behave when the earth began to move. This mentorship ensured that the apprentice understood the principles behind the techniques. He learned the why, not just the how. This was the crucial difference between a mere laborer and a true master builder. A laborer could follow a template, but a master builder could look at a new site, assess the local stone and soil, and adapt the timeless principles to these unique conditions. He possessed a flexible intelligence that could translate universal laws of physics into a specific, localized solution. The survival of a city's temples and homes for centuries depended on this unbroken chain of wisdom, passed directly from one generation of skilled hands to the next. The true foundation of every earthquake-resistant marvel was not stone or wood, but this irreplaceable human knowledge, patiently cultivated and fiercely protected across the ages. High above the bustling streets of modern Tokyo, a 5-story pagoda has stood since the time of the samurai. It has weathered typhoons and withstood the force of earthquakes that have flattened contemporary buildings, and its secret lies not in its rigid frame, but in a single, suspended column at its heart. This is the Shinbashira, the pagoda's dancing spine. This central pillar is the masterstroke of the entire design, a free-hanging pendulum that descends from the very top of the structure, often not even touching the ground. When an earthquake strikes, the flexible wooden frame of the pagoda begins to sway in one direction, but the heavy shinbashera, suspended by chains or beams from the roof, resists this initial motion due to its own inertia. It begins to swing in the opposite direction, acting as a massive, rhythmic counterweight. This creates a phenomenon known as dynamic damping, where the sway of the building and the sway of the pillar are deliberately out of sync. The two opposing motions clash and cancel each other out, transforming the violent, jerking energy of the quake into a gentle, rhythmic rocking. The destructive force is quite literally absorbed by this internal dance, preventing it from ever reaching a level that could splinter the wooden joints. The entire structure groans and creaks as it moves, but it does not break, a testament to an engineering solution that controls chaos not through resistance, but through a perfectly timed opposing response. This brilliant use of a counterforce required no nails or metal fasteners. The entire pagoda is an intricate puzzle of interlocking wood, held together by supremely sophisticated joints that allow for just enough flex and movement. Each joint acts as a miniature shock absorber, its subtle give and take working in concert with the great pendulum swing. The shinbashera does not hold the building up, it holds it together by keeping its dance in check, a timeless lesson in achieving stability through controlled, intelligent movement. A building with a single pillar is a gamble, but a building with 100 is a conversation. This principle of redundancy was a cornerstone of ancient seismic design, creating structures with not just one but many paths for safety. Instead of relying on a few critical supports, they engineered entire networks of load-bearing elements, from the dense forests of columns in an Egyptian hypostyle hall to the multiple, interlocking walls of a Roman apartment building. The goal was simple yet profound: to eliminate any single point of failure. In a typical modern structure, if a crucial support column fails, the load it was carrying has nowhere to go. This can trigger a chain reaction, a progressive collapse where the failure of one element overloads the next, leading to a swift and total downfall. Ancient engineers designed their buildings to prevent this domino effect at all costs. They created a redundant system where the weight of the structure was shared communally. If an earthquake shattered one column in a hypostyle hall, the immense stone ceiling above did not come crashing down. The load that column had been carrying was immediately picked up and redistributed by the dozens of neighboring columns. The structure might be wounded, but its core integrity remained, allowing people to escape and the building to be repaired. This was architectural teamwork on a grand scale. Think of it like a group of people carrying a heavy platform. If one person stumbles and lets go, the others can quickly adjust their grip and bear the extra weight, preventing the platform from falling. The ancient builders applied this same logic to stone and wood. In a Roman insula, a multi-story residential block, walls were not isolated. They were interconnected, forming a web of support. The failure of one wall section would see its responsibilities transferred laterally to the adjacent walls, which were designed to handle that extra, temporary burden. This design philosophy required a deep understanding of how forces flow and distribute themselves through a network. It meant building with a generous overcapacity, ensuring that every element was part of a supportive community, ready to catch its neighbor should it fall. This inherent generosity of structure, this built-in safety net, is what made these ancient buildings not only strong, but forgiving and ultimately far more resilient to the unpredictable chaos of a shaking earth. The wisdom of those ancient builders did not vanish with their civilizations. It lay dormant in the stones, waiting for modern science to catch up. For much of the 20th century, mainstream engineering pursued a philosophy of rigid strength, designing buildings to stand perfectly still against the Earth's force. It was a battle of brute force, and the Earth, time and again, proved stronger. The turning point came when engineers, armed with new instruments and a growing record of seismic failures, began to look back. They realized that the very principles they were beginning to codify into law, concepts like base isolation and energy dissipation, were not new inventions. They were rediscoveries. The ancient practice of placing a building on a layer of shifting stones is now a formalized technology called base isolation, where modern structures rest on massive rubber and steel bearings that allow them to slide safely during a quake. The intricate wooden joints that groaned in a Japanese pagoda, dissipating energy through friction, have their direct counterpart in the steel dampers and viscous fluid shock absorbers we install in skyscrapers today. We now call it ductile design, the ability of a structure to bend and deform without breaking, a quality inherent in every flexible stone wall and every swaying timber frame. What was once an intuitive art is now a rigorous science, but the foundational truth remains identical. The most profound validation for these modern codes comes from the ancient structures themselves. When computer models simulate an earthquake against a 2,000-year-old temple, the results are astonishing. The building's calculated movements match its real-world survival perfectly, proving that the empirical methods of the ancients were not just lucky guesses, but scientifically sound solutions to a timeless problem. We are not inventing a new science, we are finally learning to speak the old one, translating an intuitive mastery of physics into the precise language of modern engineering. This journey back to the future reveals a humbling truth that the path to resilience was not only discovered long ago but built to last. It is a seductive idea that these ancient marvels were built with some forgotten super science or tools from beyond the stars. This myth, however, robs their true creators of the immense credit they deserve. The reality is far more compelling. There was no magic crystal, no alien blueprint. The secret was a profoundly human one, a triumph of relentless observation and practical intelligence honed over countless generations. These builders were the ultimate empiricists, their laboratories the construction sites and ruins of their own cities. They learned by watching which buildings fell and which ones stood, then adapted their methods accordingly. This was a slow, cumulative science, passed from master to apprentice in an unbroken chain of lived experience. The genius was not in possessing advanced technology, but in wielding simple tools with an almost supernatural level of skill and understanding. They did not have computers to model stress points, so they developed an intuitive feel for how forces flow through stone and timber. They could not manufacture synthetic dampers, so they used the earth itself, creating friction with gravel and flexibility with perfectly fitted joints. This was engineering at its most fundamental and brilliant, a deep collaboration between the human mind and the materials of the natural world. To attribute their work to a lost super science is to miss the point entirely. Their achievement is a testament to what humanity can accomplish with patience, keen observation, and a deep reverence for the laws of physics. The real story is not one of a mysterious, lost power, but of a hard one, enduring wisdom that we are only now, with all our modern instruments, beginning to fully comprehend and formally replicate. Their legacy is not a secret to be uncovered, but a method to be learned from, a reminder that the most profound solutions are often born from simplicity, not complexity. A building's roof is its crown, but during an earthquake, a heavy one becomes a weapon. The immense weight of a rigid stone or concrete roof high above the ground creates a dangerous pendulum effect. When the ground shakes, this massive top section whips back and forth with tremendous force. its inertia pulling the walls it rests upon out of alignment and leading to catastrophic failure. Ancient engineers understood this threat intuitively. Their solution was not to reinforce the roof to make it stronger, but to make it lighter. Across the globe, they consistently chose lightweight, flexible materials for their coverings. In many Asian temples, you find sweeping roofs of wooden shingles. Across Europe and the Pacific, thatch was a common choice. Even when they used tiles, they were often thin and carefully interlocked. This was a deliberate strategy of weight reduction at a critical point. By minimizing the mass at the very top of the structure, they dramatically reduced the inertial forces generated there during a tremor. The whipping effect was softened into a gentle sway, but their genius did not stop at simply making the roof light. In many designs, the roof was not rigidly locked to the walls. It was designed to have a degree of independence, resting on flexible supports or in a framework that allowed it to move slightly out of sync with the walls swaying below. This concept of differential movement was a masterstroke. It meant that when the walls rocked one way, the roof could shift another, preventing a destructive tug of war at the connection points. The entire structure could breathe and flex as a unified yet dynamic system. This careful attention to the uppermost element, this willingness to sacrifice the appearance of monolithic solidity for the reality of life-saving flexibility, completed the ancient building's defense from its deep foundations all the way to its sheltering peak. A temple aligned with the rising sun was not merely a matter of aesthetics. It was a direct plea to the gods for stability in a trembling world. For ancient societies, the Earth's violent shudders were not random geological events. They were messages from powerful, often temperamental deities. This spiritual interpretation of earthquakes provided a profound, unifying motivation that went far beyond simple survival. The immense labor of quarrying, shaping, and placing multi-ton stones with such precision was fueled by a collective belief that they were not just building a shelter, but constructing a sacred vessel, a place worthy of divine protection. This cultural imperative meant that corners were not cut, and the most resilient, time-tested techniques were not just preferred, they were mandated by faith. The practical need to prevent collapse was seamlessly woven into the spiritual need to honor and appease the gods of the earth and underworld. This is why the orientation of a temple was so critical, its axis carefully calculated to align with celestial bodies or sacred mountains, creating a harmonious link between the heavens, the human realm, and the world below. A building in perfect alignment with the cosmos was, in their view, a building in balance, and therefore a building that would stand. The symbolic strength of shapes played an equally vital role. The pyramid, for instance, was not just a stable geometric form. It was a representation of the primordial mound from which life emerged, or a staircase to the gods. Its incredible stability was both a physical fact and a spiritual affirmation. This cultural dimension provided the social and economic justification for projects that would otherwise seem impossibly ambitious. Why would a society invest generations of labor into moving stones that fit together with paper-thin precision? Because the stability of their world, both physical and spiritual, depended on it. The drive for survival and the desire for divine favor became one and the same, channeling human ingenuity into a form of architecture that was as much an act of worship as it was a feat of engineering. Yet the silent strength of interlocking stones was only one part of the material story. Alongside these masterpieces of dry construction, ancient cultures were also pioneering a form of material alchemy, developing sophisticated mortars and binders that added a crucial element of flexibility. The goal was not to create a rigid, unbreakable glue, but a living, breathing matrix that could accommodate movement. The Romans, for instance, perfected a concrete that remains a marvel of chemistry. Their secret ingredient was volcanic ash, known as pozzolana, which they mixed with lime and rubble. This was not the brittle concrete of some modern failures. The volcanic ash created a chemical reaction that produced a crystalline structure with a unique quality, a degree of plasticity. When stressed, this Roman concrete could develop tiny, internal microcracks that actually dissipated energy, preventing the formation of a single catastrophic fracture. It was a material that could flex and give, then heal itself over time as the lime continued to react with moisture in the air. This was resilience engineered at a molecular level. A similar principle was discovered half a world away in ancient China. There, builders created a mortar of legendary strength and flexibility by mixing standard lime with an unexpected organic ingredient, sticky rice soup. The amylopectin in the rice acted as a natural polymer, creating a composite material that was both incredibly strong and remarkably shock-absorbent. The resulting mortar was tougher and more flexible than pure lime, bonding bricks and stones with a grip that could sway with seismic forces instead of shattering. These were not primitive paste recipes. They were precisely calibrated composite materials, their ratios refined through generations of trial and observation. A mortar that was too rigid would crack and crumble, while one that was too weak would simply fail. The master builders found the perfect balance, creating binders that held everything together while still permitting that vital, life-saving give. This development added a powerful new layer to their architectural toolkit, allowing them to build monolithic structures that behaved not like a single, brittle block, but like a cohesive, flexible body. That wide base and narrowing peak of a pyramid is not just an iconic shape, it is a masterclass in structural physics. Ancient engineers consistently designed their most important structures to be broader at the bottom and tapered toward the top, a deliberate strategy to pull the building's center of gravity downward. Think of a child spinning top. Its low, heavy core is what allows it to wobble and dance without falling over. The pyramid works on the same principle. By concentrating the majority of its immense mass in the lower levels, it creates an incredibly stable form that is profoundly difficult to tip over. When an earthquake's lateral forces try to push the structure sideways, that low center of gravity acts as an anchor, forcing the building to rock gently on its wide base rather than toppling. This geometric wisdom was applied everywhere, from the sloping walls of medieval castles to the majestic ziggurats of Mesopotamia. But what about the walls themselves, the tall, flat surfaces that could buckle under pressure? For this, ancient builders developed another brilliant feature, the buttress. These projecting supports, looking like stone fins pressed against a wall, were strategic reinforcements designed to combat a specific threat, lateral thrust. During an earthquake, a tall, freestanding wall wants to bend and fold outward. A buttress acts as a powerful brace, absorbing that sideways push and channeling it safely down into the ground. It turns a weak, flat plane into a strong, articulated form. The true elegance of these solutions lies in their simplicity. A builder did not need complex mathematics to lay them out. With nothing more than measuring chords and a weighted line, they could establish the perfect taper for a wall or the ideal angle for a buttress. This was engineering based on observable, physical principles, a clear grasp of static equilibrium achieved with the most fundamental tools. They understood that a structure in perfect balance with the forces of its own weight was a structure ready to meet the unpredictable chaos of a shifting Earth. These solutions were not confined to one corner of the world. A global tapestry of seismic wisdom was being woven simultaneously by cultures that had never met. In the highlands of Anatolia, Turkish builders developed a unique wooden skeleton known as the himizes. This was not a solid wall of timber, but a flexible lattice framework. The wooden beams were intricately joined to create a box-like structure that could sway as a single, cohesive unit during a tremor, its joints groaning as they dissipated the earthquake's energy through friction. Far to the west, in the Bronze Age citadels of Mycenaean Greece, a different kind of genius was at work. To span openings in their massive stone walls, they perfected the corbelled arch. This technique involved stacking layers of stone, with each layer projecting slightly inward over the one below until the two sides met at the top. It was a false arch, creating a strong, triangular-shaped opening that effectively channeled the weight of the wall above down and around the empty space, preventing a weak point from forming. The Mycenaeans built gateways that have stood for millennia, their corbelled arches a testament to their understanding of load distribution. The Japanese masters of wood engineered pagodas with their floating central pillars. The Inca, with their polygonal stonework, created walls that moved as a single skin. Each civilization, working with its own local materials and cultural aesthetic, arrived at a remarkably similar set of principles. They all embraced flexibility over rigidity. They all found ways to dissipate destructive energy, whether through rocking foundations, grinding stone joints, or swaying wooden frames. And underlying every chisel mark and timber joint was a profound respect for the natural forces they could not control. This was not the story of one isolated genius, but a fundamental human response to a universal threat. It reveals a shared, global intelligence, a collective awakening to the simple truth that to survive the Earth's power, you must learn to move with it.